All right, so I just wanted to go through a couple of the week 9 topics in ALEKS, just to make sure that we are comfortable with some of the things that we need to do. So for example, one of the first topics here that you're going to have to get through is drawing the Lewis structures for simple organic compounds. And this is sort of an extension of what we learned earlier with Lewis structures. The only difference now it's applied to organic chemistry. So this one says draw the Lewis structure for acetic acid, gives you the formula, and then it tells you that there's one hydroxy group and one carbonyl group. All right, so what is the hydroxy and the carbonyl? So the hydroxy group is an OH, so the O and the H connected together, and then the carbonyl is the C double bond O, right? And then your remaining bonds to carbon as lines. Remember, carbon likes to form 4 bonds. The hydroxy, which is the OH, this line there just means that it's connected to something else, right? So that this is what defines these particular groups, and you'll see them in the video, the very last video in the week 9 module that talks about the different functional groups. Okay, so I'm going to say the functional groups video. So using this information, we can go in and we can draw the structure for acetic acid. Okay, so here we have our drawing tool, which we've used before. So we have C2H4O2. And remember your rules for drawing Lewis structures. Usually when you see carbon in the structure, you want to stick that in the middle. So we're going to put carbon here. And we want to have a bond to another atom. And there are 2 carbons, so guess what? Those carbons should probably go together. We have 4 H's and we have 2 O's. Now remember that there's a hydroxy group, so there's an OH, and the only place that OH can be connected would be to one of these carbons. So let's add a bond, and then we're going to place an OH on there. So we have an OH. I just typed in OH. Let's see. Get the the OH drawn. All right, so there's my, I'm going to put the OH on this carbon. I could put it on the first one if I wanted to. But let's put it on this one. That's where we started. So we have an O, and then that O is going to be connected now to an H, right? So we need to put that bond in. And we're going to add our H over here, right? So that's the OH, but sometimes you see the OH linked together or the O connected to the H. And then we also need that carbonyl, which is that C double bond to the O. Let me remind you what that is. All right, so we just put that OH in. Now we're going to have to draw the C double bond O. So where does that C double bond O go? Is it going to go on this carbon on the right? Is it going to go to the one on the left? Well, remember, we also need to have our 4 H's, right? So right now we have 1 H drawn in. We still need 3 other H's. So if I were to put the C double bond over here, so let's do this. We'll put 1 bond, we'll do another one, and then we're going to add that O to it. So there it is. And then you can see your carbon has 1, 2, 3, 4 bonds. Oxygen has 2. This oxygen up here has 2 as well. This carbon here on the left only has 1, so it needs 4 more. I'm sorry, it needs 3 more. So 1, 2, and then 3. And guess what? Those are going to be to H's. Right, so we got our H. Got an H over there, and I've got an H on the bottom. So there's our C with 1 sorry, we have two C's. We have 1, 2, 3, 4 H's. We have two O's. Then we have in our structure the hydroxy, the OH group, and then we also have the carbonyl, the C double bond O. We also want to include the lone pairs, so don't forget that we'll need 2 lone pairs on the oxygen to give it its octet, and we'll need 2 lone pairs on that oxygen as well. If I check, that's your correct structure. Okay, and then in our next one, we have this question where we're looking at identifying constitutional isomers. All right, and then what isomers are, and you'll see this in the videos as well. Okay, these are just molecules that have the same molecular formulas, but different structures. Okay, so the components are the same, right? So what they're made up of is they have the same number of atoms and types of atoms, but how those are connected are different, and that gives them different structures. So if we have this molecule here, so we have a molecule that looks like this. All right, so we need to interpret this first of all. So remember, there's a carbon here at each, where 2 lines meet. If there's no other atom shown, there's a carbon, which means there's a carbon down here. There's a carbon over here as well. So we have a total of 1, 2, 3 carbons. And then we can explicitly see our 2 O's. We have 2 O's. So how many H's are in this? Well, we need to fill in the number of bonds to carbon to give it a total of 4 bonds. And we fill in those bonds with H's, right? In these skeletal structures, the H's are not explicitly shown. So there's a carbon here, right? That right now has 2 bonds shown to it. So the remaining 2 bonds will be to hydrogen. This carbon down here, the lower left, also needs 2 bonds to hydrogen to give it a total of 4 bonds. And the one on the right also needs 2 more. So we have a total of 2, 1, 2, 3, 4, 5, 6 H's in that structure. So what we need to do is to go through and look at these options, and we need to decide which of those has, so which other structure has the same components, has the same number and types of atoms. Right, so this is where interpreting your line angle or your skeletal structure is going to be important. So for example, if we look at this one here on the upper left, and I'll draw that one underneath. So I have an OH like this. I have another OH down here. All right, so if I look at my number of carbons now, I have 1, 2, 3, 4 carbons. So right away, I don't have the same number of carbons, right? So so that's not going to be an isomer because it's not made up of the same. I don't even have to go any further than that. If I look at the one on the right, the upper right side, so that's this one. So I have an OH like this. I have a double bond, an OH there. So if I look at my number of carbons, I have 1, 2, 3. If I look at my O's, I have 1, 2 O's. I look at my H's now, I have 1, 2. The carbon up here needs 3 more. This carbon here already has 4 bonds, right? It's got 1, 2, 3, 4. It doesn't need any more H's. This carbon here right now has 1, 2, 3, so it needs 1 more bond to an H. So if we could add up all our H's, we have a total of 1, 2, 3, 4, 5, 6 H's. And if we compare that to our one on top, C3H6O2, right? That would be a constitutional isomer. It's got the same number and types of atoms, but obviously this structure is different than this ring structure, right? So that would be an option. You need to go through and look at the other ones as well. All right, so in this question, we're looking at interpreting our condensed chemical structures. So we have a CH3, single bond to a CH, double bond to a CH2, right? So that's a condensed chemical structure for this molecule called propene. We need to identify the following. So the number of carbon-carbon single bonds, right? So a carbon-carbon single bond is just a single line. And sometimes the way that condensed structures are written, it may look like, for example, this bond here is connecting a carbon to H's. Now remember, that really can't happen because hydrogens can only form one bond. So really what this means is that it actually looks like this, right? So we have a carbon single bond there. We also have a carbon to carbon double bond. And then the number of carbon hydrogen single bonds, well, we can expand out our structure. If I draw just the carbon skeleton, that's what it looks like, 3 in a row, 1, 2, 3. And then on this carbon here on the left, I have 3 H's. So 1, 2, 3, I fill in those H's. The second carbon has 1 H attached to it. And then the carbon on the right has 2 H's. So 1, 2. So I have a total of 1 carbon hydrogen, 2 carbon hydrogens, 3, 4, 5, 6 carbon hydrogen bonds. Okay, so when you have your condensed structural formula, the best way to actually convert it and to figure these out is to expand it out, draw all of the atoms, all of the bonds, and that way you'll explicitly see what types of bonds are present. All right, so in this question, we're looking at interpreting the skeletal, or sometimes it's called a line angle structure. Okay, and this is the most efficient way to draw organic molecules, organic compounds. But we need to know what the structures actually mean, all right? And when you go through the videos, I show you exactly the different types of structures. We have the molecular formulas or the molecular structures, the Lewis structures, which give you the most information. That's the expanded structural formula. We can condense that down into the condensed structural formula, and then we can make that even more condensed by these skeletal structures. So if I have something that looks like this, okay, what does this actually mean? Well, we can go ahead and expand this out. So we're going to draw all of the explicit atoms and bonds. So we have an oxygen. Remember where lines meet, there's a carbon. There's a carbon there. There's a double bond to another carbon underneath. That's bonded to an O. That's bonded to a carbon on the right. It's a single bond to a carbon on the top and a single bond there. And then all I need to do is to fill in the remaining bonds to carbon, because carbon likes to have 4 bonds, and we'll fill those in with hydrogen. So this carbon here right now has 1, 2, 3, so it needs a 4th bond to H. Same thing with this one, right? This has got 1, 2, 3 bonds, so we need a 4th one to an H. This carbon here has 1, 2, so it needs 2 more H's. And this one here is in the same boat. It's got 1, 2 bonds, so it needs 2 more H's attached to it. All right, so I've taken my skeletal structure and I've converted it into an expanded structural formula that shows me every atom and every bond. So now we need to figure out what the molecule's chemical formula. So that's just where we list the atoms and the number of atoms that we have. So I have a total of carbons, 1, 2, 3, 4 C's. I have 1, 2, 3, 4, 5, 6 H's, and I have 1, 2 O's. Okay, so that'll be my molecular chemical formula. That's the molecular formula. And then how many CH3, CH2, and CH groups are in this? So CH3 would mean that we have a carbon and 3 H's attached to it. A CH2 would mean that we have a carbon and 2 H's attached to it. And then a CH would mean that we have a carbon and just one other H attached to it. All right, so if we look at the structure, we'll highlight the different types. So I have a CH over here. I have another CH. And then I have a C and 2 H's. That's a CH2. And that's a CH2 down there. All right, so this here is a CH2. This is a CH2. This is a CH. And then that's a CH. We have no CH3s. Obviously, you can't see a carbon connected to 3 H's. All right, so in the next question, we'll take a look at identifying the main chain of branched alkanes. All right, so here it says tag each atom in the main chain of the 2,3 dimethylpentane. So when it comes to the nomenclature, naming your organic compounds, they're all named systematically. And the last name actually tells you, so the pentane here tells you the longest chain, the longest continuous carbon chain is 5 carbons long, right? That's where the pent comes from. So we need to find the 5 long, 5 carbons in a row. It doesn't have to be a straight line. It can snake around. It just needs to be 5 continuous carbon. All right, so if I look at my structure, if I start on the left, that's normally where we gravitate. We have 1, 2, 3, 4, 5. Okay, so that makes sense. If I start at the top, I go 1, 2, 3, 4, 5. So that makes sense. If I start on the right, I go 1, 2, 3, 4, 5. So which way is the correct way? Because I can get it from different directions. Well, the first part of the name also tells you something important. So 2,3 dimethyl. So this means that we have 2 methyl groups. Okay, and a methyl is a CH3. And these are connected to carbons 2 and to carbon number 3, right? So we have a CH3, and this CH3 is a C and 3 H's that looks like that. And that needs to be connected to carbons 2 and 3. So now if I look at my numbering, if I start here on the left side, that's carbon 1, that's carbon 2, and there is a CH3 attached to it. This is carbon 3, there's a CH3 attached to it. So I have a 2,3 dimethyl 4,5. And that's your pentane. So that would work. If I start on the top, carbon 1, carbon 2, there's a CH3 attached to it on the left. Carbon 3, there's a CH3 attached, 4, 5. So that'll work as well. If I start on the right side, 1, 2, 3, there's a methyl group attached to that. Carbon 4, there's a methyl attached. So if I start on the left side, the methyls are attached to carbons 3 and 4. And that's not what we have. We have a carbon or a methyl on carbons 2 and 3. All right, so you need to be able to establish the longest continuous carbon chain when we name our organic compounds systematically. All right, then we're going to take a look at identifying organic functional groups. Okay, so again, make sure you watch the last video in the week 9 videos. So it says name the family to which each organic compound belongs. First answer has been filled in. So this first one here, usually your functional groups would be a collection of atoms. or types of bonds that indicate a special organic family. So for example, this first one, typically your functional groups are atoms other than carbons and H's. That's how you can quickly gravitate towards them. So this first one here, we have a C, O, double bond O, OH, CH2, and a CH3, right? So right away, we can see this looks different. And then also this looks different down here, right? So all of these would count as one functional group. That's the COOH functional group, or sometimes it's written as COOH. I just did it backwards, but it's the same way, like this. That's the carboxylic acid functional group. All right, so if we do the second one, this one down here, so I have a CH3 connected to an O, a C, an H, and two CH3s above and below. Right now I have, looking, again, we're trying to, first of all, identify any atoms other than carbons and H's. There's an O, and when this O is between two carbons, like this, that tells us that this belongs to the family of ethers, or an ether would be this functional group. Okay, so as you go through that video, it'll show you the different families or functional groups that you can use to identify what they belong to. All right, so the next thing we're going to take a look at is cis-trans isomerism. So this is a special type of isomerism that can exist when the atoms in different molecules are the same. Also, the order in which the atoms are connected is the same, but what's different about them is the orientation of those atoms in space is different. So this is an example of what's known as geometric isomerism, is another term that you'll see. So in order for cis-trans isomerism to exist, typically what we need is a carbon-carbon double bond. And the remaining bonds to each of these carbons here need to be to different things. Okay, so the remaining two bonds need to be to different things, whether that's H's and chlorines or a longer carbon chain. And the same thing applies to this other carbon of the double bond, right? The remaining two bonds must be to different things. So what do I mean by that? Well, let's take a look at an example. We'll do the first one here in the upper left. So I have a C, double bond C, there's an OH on top, an OH on the left, a CH3 on top on the right, and then a CH3 over here. So we're going to look at each of these carbons. So we'll take a look at this one first. What we're saying, the remaining two bonds to that one needs to be to different things. So this remaining bond here is to an OH, and the last bond is also to an OH. These are not different, right? These are the same. And just by looking at that, this cannot be cis-trans. Okay, so we can just, that's not possible for that. We don't even need to look at the other carbon because we've already established that this first one here makes it impossible. We can confirm, well, there's a CH3 attached to this one. There's another C, these are also the same. So again, we cannot have cis-trans there. If we take a look at the one underneath it, okay, so if I have something like C, double bond to a C, I have a Cl, a CH3, and then I have a CH3, and then a Cl. All right, so we'll do the same thing. This carbon here on the left side it's bonded, the remaining bonds, single bonds are to a methyl, CH3, and to a Cl, right? These are different. Okay, so that means, yes, we can possibly have cis-trans. Then we also need to look at the other carbon, because the criteria needs to be satisfied for both of these carbons. So this carbon is connected to a Cl and a CH3. These are different. And because now both carbons of the double bonds are connected to two different things, yes, cis-trans is possible. In this molecule. Okay, so you have to look at both carbons of the double bond that need to be connected to two different things. All right, and then the last one we'll take a look at is where reactions are concerned. So knowing the different functional groups is one thing, knowing how to name them generally is important. What's even more important is once we know what functional groups are present, what types of reactions can they undergo? And as we'll see as a common thread throughout all of organic chemistry is once you identify the functional group or the family, that particular molecule will always undergo a certain set of reactions. It doesn't matter how big or small the molecule is, as long as you have that particular functional group, it will always undergo a certain set of reactions. And that's the pattern side of organic chemistry. So let's take a look at an example. So we have this molecule, and we're going to react it with water under acidic conditions, right? So that's what all this stuff means when we see the reactions. So when you see H plus above the arrow, this just means that we need an acidic conditions, or in this case, an acidic catalyst, because catalysts produce protons. I'm sorry, acids produce protons, H pluses. So we have here, what type of molecule is this one? Well, we have a carbon-carbon double bond, okay, which makes it an alkene, and then we're adding water to it, H2O. So this would be an example of a hydration reaction where we add H2O. Now, when you think of H2O in organic chemistry, you want to think of it as H connected to OH, right? Because that's what water is made up of. And when we think about it this way, and we're adding water to something, well, guess what? The H, and when we have an alkene present, all the action's going to happen at the carbons of the double bond. So we're going to add something to that carbon. We're going to add something to that carbon, right? That's where the reactive portion of the molecule is. Specifically, what are we going to add? Well, we're going to add an H, and we're going to add an OH. So when H goes to one carbon of the double bond, the OH goes to the other carbon of the double bond. So as a result of that, my double bond then gets converted to a single bond. And now I've stuck an H onto one and an OH onto the other. I apologize about the background noise. There's some construction going on here on campus. So as a result, I end up making now a molecule that has an OH group in it, a hydroxyl group. Guess what? That's an alcohol, right? So when you take an alkene and you hydrate it, you end up producing an alcohol as the product. In some cases, you might be asked to provide the reactant if you're given the product. So for example, here we have something reacting with H2O under acidic conditions to give you your OH, right? So now we're given the product, that's our alcohol. That's this thing. So what we need to decide is what the alkene is, right? So we just talked about that being the reaction involved. So alkenes have carbon-carbon double bonds. So we can draw that. So I have carbon double bond. And looking at my product here, I have a total of how many carbons in it? I've got 1, 2, 3. So I just need to add another carbon to it. And I'm just going to fill in my remaining bonds to H's. So this carbon here needs 2 more H's. This one needs 1 more H. And the one on the right needs 3 more H's. All right, so that could be a reactant. And if I want to draw the skeletal structure for this, well, I have 1, 2, 3 carbons, 1, 2, 3, and a double bond there. And that's it. So if I draw my my reactant, you got 1, 2, 3. I'm going to add a bond to this second bond. Here we go. And if I check this, right, that can be a possible reactant where I add water to it, and H goes to the carbon of a double bond, the OH goes to the other carbon of the double bond. I could just as easily draw it this way with a double bond on the other side. It would be the same molecule.